perform a lab where we're going to try to verify Newton's second law, which essentially says the net force is equal to the mass times the acceleration. Remember, we did Newton's first law, says an object at rest stays at rest until acted upon by an unbalanced force. An object in motion stays in motion, and a straight line constant speed until acted upon by an unbalanced force. We also call that the law of inertia. Sometimes we even call it the law of equilibrium, right? Balanced forces, the law of balanced forces. Newton's second law is, well, you could call it, if you wanted to, the law of unbalanced forces. There's a net force, and that net force is equal to the mass times the acceleration, or at least so we think. The net force is equal to the mass times the acceleration. That's what we're going to try to verify today. This is the way you're going to set up this lab. You're going to have two masses that are connected by a string, and a string is going to go around a pulley. Mass number 2, and it's important that you label these correctly, mass 1 and mass 2. Okay, this is mass number 2, this is mass number 1. Mass number 2 is a dynamics track, one of those smart carts that you've used for the other labs that you've done that electronically transfer data to your phone. Okay, that's a smart cart, and that's going to be on a track. Some of you are going to have wooden tracks like this. Some of you are going to have metal tracks like this. You'll see where you put them, okay, in the slots. Okay, the metal track's easy. The wooden tracks, there's 2 sets of slots, but you'll see which slots match up easily with the wheels on the dynamics cart. So whatever track you use, that track is going to be on a desk. You're going to have a pulley on the end of the desk, and you're going to have a string connecting the smart cart, which is on your track. Okay, it's the string that's connected to the smart cart around the pulley, which is on the desk, and connected to a mass, a relatively small mass. You can use a different mass than you use. That's okay. There's no specific number that I want you to use, but we want it to be relatively small. So I've got some mass sets up here. These mass sets range from, what is this, 10 grams all the way up to a kilogram. Okay, we don't want to use 10 grams, but something like this would probably work. Something like 100 grams. Grab a mass, 100 grams, 200 grams maybe at the most, and attach it to the string at the other end hanging off the edge of the desk. Does that make sense? So maybe maximum 200 grams. I'd probably even stick with a little bit less than that, to be honest. Maybe 100 grams. If we run out of masses that you want to use, we've got more in the back there. Just let me know and I'll get you another one. Okay, so that's the way it's going to be set up. Now, there's instructions over here in the little handouts over here as to how to use the smart carts and how to connect them if you forget how to do that. Okay? You guys remember using those? If you forget the details of it, you can always check those instructions. Remember, when you go into the app, the SparkView app on your phone to collect the data, there's a few options that you can pick. Today, you're going to pick velocity, okay? As opposed to selecting position to measure position, you're going to select velocity to measure velocity. Does that make sense? If you have any questions about that, you can ask me when you're doing it. So your data is going to look like this. You're going to have M1, which is the hanging mass. And that's going to be somewhere in the range of 100 grams. You're going to have M2. That's going to be the mass of the dynamics cart. And the mass of the smart cart, the dynamics cart, is printed right on it. So you don't even need to measure that. It's going to be printed in grams, however. You're going to want to convert that to kilograms. You're just going to do that by dividing by 1,000, right? If it's 294 grams, it's 0.294 kilograms. Make sure you record it in kilograms. Make sense? Now, the next thing that you're going to have is your data table of velocity versus time. Time in seconds and velocity in meters per second. That's going to come from you exporting your data to Google Drive, then sharing that data with your partners, making a copy, remember this? Okay, exporting your data to Google Drive, sharing your data with your partners, everybody makes a copy, and then you tweak it to look like this with time and velocity. Okay? So that's going to be your table, time and velocity. Then you're going to plot a graph. The graph is going to be velocity versus time. Velocity on the y-axis, time on the x-axis. And that should give you a nice straight line on your graph. You will have Google Sheets plot a trend line, which should be linear. And then you'll have Google Sheets display the equation. The equation might look something like this: 0.714x plus 0.003. Yours won't be those numbers. The slope of this graph is what? 0.714, 0.003. 0.714. That's the slope of the graph. What does the slope of a velocity time graph represent? Acceleration. So you've just found the acceleration of this smart cart as it's rolling along this track on top of a desk to be 0.714 meters per second squared. Depending upon the mass you use hanging over the edge, that's what's going to affect what the acceleration is, right? The higher the mass, the higher the acceleration is going to be. Make sense? All right. Whoops. Then you're going to scroll down in your template and fill in these tables here. Okay, you can fill in these tables. You should be able to, I think, do it on Google Docs. It shouldn't be a big issue because there's not a whole lot of calculations to do there. But if you do want to write it out by hand, take pictures of it, insert it into the document in this table, that's okay too. Got it? All right, so what we're going to do in the first one is M1 plus M2. M1 plus M2, those are the two masses that you measured, right? The mass of your dynamics card and the mass of the hanging mass. M1 plus M2, in other words, the total mass times acceleration. That should give us the net force, right? The total mass times acceleration should give us the net force. Show that work. Don't just give me a number here. Show the work. M1 plus M2 times acceleration gives me whatever the number is. Show that work. Now over here, you're calculating the force of gravity. M1, which is the hanging mass, times 9.81. Don't worry about a negative sign there. Just make it M1 times, in kilograms, times 9.81. Get what you get. Okay, got it? Show that work as well. M1 times 9.81 equals whatever it equals. What should you notice if Newton's second law is correct? If F net is equal to the sum of the F net is equal to mass times acceleration. What should you notice about these two forces? What should you notice about these two forces? The net force is mass times acceleration, right? What causes the net force on this? What's causing the acceleration here? Gravity on the hanging mass, right? So if I multiply the hanging mass times 9.81, that should also give me the net force, the same force. So you should notice that these two forces are the same. Now, realistically, they're probably not going to be exactly the same. There's always a little bit of error when we're doing an experiment, right? It doesn't matter what level, whether it's grade 11 physics or whether it's, advanced research at a university. It doesn't matter. There's always going to be some error. So what we're going to do is answer this question: does Newton's second law hold in this experiment? If they're the same, the answer is yes. If they're not the same, the answer is no. But we have to have a range of error that we accept as being okay. So what we're going to do is calculate a percent difference to determine whether these two numbers are close enough. Have you guys done a percent difference calculation in chemistry or in Science 10? There's various ways of stating that, but they all boil down to the same basic way. Just might look a little bit different. Your percent difference is your actual minus your theoretical over your theoretical times 100. Have you guys seen that before? Yes? Actual minus theoretical over theoretical times 100. So in this case, we would say the actual is what? What would be the actual? What would be the theoretical? Theoretically, this force that we got from our graph should equal the value that we got in the first place, which is just m1 times gravity, right? So this is going to be our theoretical value, and this is going to be our actual value. Does that make sense? So whatever you get here, subtract whatever you get here, divide it by whatever you get here, and then multiply the whole thing by 100. Why do I have those little vertical lines there? What does that mean? Absolute value just means you're going to get a positive number for your percent difference. Okay, whether it's a little bit above, a little bit below, it doesn't matter. You're going to get a positive number for that percent difference. Now, what we're going to say is if that percent difference is less than 10%, that's going to be our magic number. If it's less than 10%, we're going to say, yeah, it's okay to assume that Newton's second law held here, that these two forces were close enough that they're really the same. It's just experimental error probably that led us to the small difference. If it's bigger than 10%, we're going to say, that's a little bit big. We're going to say that Newton's second law does not hold. Does that make sense? Now remember, your little conclusion here has to be consistent with your data. So if you get a percent difference of 12%, that's okay. But your conclusion has to be, it was not verified. If you get a percent difference of 9%, good. Your conclusion will be that Newton's second law was verified. So just make sure, you can get full marks whether it is verified or not. Just make sure that your conclusion is consistent with your data. Okay? Now I say that as a conclusion, but we're not doing a separate conclusion for this. You're just going to answer this as an analysis question. That make sense? Just fill in the blanks like you always do. Okay? Except that this time the blanks look a little bit different, that's all. Now, that's exactly what you're going to do. You're going to actually repeat that, though, for a second trial. So you're going to do that same analysis twice with two different trials, with two, listen carefully to this, with two different hanging masses. So if you use 100 grams in the first one, maybe try 50 grams in the second one, or whatever the case may be. Two different masses. Get it? Repeat the exact same thing, export that data, share it with your partners, make a copy of it, then do your thing. Make sure, just as a little piece of advice here to keep things straight, make sure that you record very carefully, very accurately, what the mass was with each trial. You don't want to mix up and use your data from trial 1 with the mass from trial 2 or something like that. Okay, so make sure that you have the mass going with the right velocity time data. The only other thing you need here is sources of error. 2 or 3 good sources of error, plus, of course, your suggestions for improvement. There's not a whole lot for this, right? It's basically data analysis, source of error. Got it?